Welcome to a new test and teardown video. This time it's a sound technology model 1700B distortion measurement system. It is from about 1979, made in USA. It was quite easy to find the manual, so I got the complete user guide and schematics and all that kind of good stuff. I started to clean this up because it's really gross. This is just sometimes some people find these in an old rusty barn somewhere, and there's probably a whole haystack on top of it, or I don't know how it is possible to make it look like this all over the place. I took a picture of the condition when I just picked it up. I should probably put in a picture like here, and you should see how nasty it really was. I used a paintbrush and compressed air on all this. So, I mean, and here a little bit of water. And down here, a little bit more water and a little rubbity nicey. And I will probably go through a little bit more cleanup. Oh, this is wild. I mean, please store your electronic instruments in a nice and good way, or just throw them out. To begin with, I don't know. You see, it really needs a lot of cleaning and lubrication. So I should start with a little open and investigate. How is it looking inside? Analyzer or generator? Is this supposed to say clickety clickety? Buffered input signal. Okay, so the input signal goes in and then this is the output or something like that. A fuse, generator fuse, mains fuse. Well, that's weird. Line selects. 230. How nice. We got a little bit of information here from Sound Technology about the model and serial number. What is that? An option. Aha. Yeah, let's see if we can figure out how to open it. Let's start with a bottom view. And the first thing that I freak out about is this fantastic design here. You gotta yell and scream a little bit with me. Look at all those shadow switches. What the hell? And also in here. And you know what? There's a little shield plate in between two layers of switches and whatnot, and they're connected, this section and that section together. Look at that. So this explains why it is really difficult to push them, and they go out this slow. And they need a little bit of clean. I'll try and spray some in, and also try to move the on-off switch, and that don't seem to work either. It's nicely shielded, the cable to the transformer, input filter and all that. Super nicely done. Look at the switches here in two different rooms for good isolation. I mean, I kind of like that design here. I got some capacitors, probably for frequency cutoffs, and they were supposed to be down there. That should not have been used. They shouldn't do this with glue. How about a little piece of metal over or something like that? And that is the fuse here for the input and the output, right? I mean, maybe they should have put this fuse here in the front, so the signal, look at all this super sexy isolation, and then signal just goes, hello, in this room. What are you thinking about that? That is some crazy misunderstanding. And the top side is really beautiful. I kind of like it with all the ICs and sockets, and okay, not all the transistors are in socket. I think that will be up to couplers or some other up to isolators or LDRs and something like that, most likely. Relays, right? And power supply is really nicely done as well. Let's try and look a little bit at that. A plus minus supply with good ICs and regulators and all that kind of stuff. So all that is super fine. I don't see any leaked capacitors anywhere. So I think I want to try and clean a few of the switches, so I should be able to power this. Yeah, I think this one should have a little clickety click, and that is not the case. None of that as well here. I took away the two knobs here so I could do a much better clean of everything, and they're now nice and fine. So the power on off switch, look at that. It's just completely broken. Something is wrong inside, and I've seen this a few times before. Sometimes you can put in a few drops of contact cleaning, and then it actually works again, but this is not the case. I need a new one. So I think after a lot of cleaning and checking, I feel lucky. So the first thing will be check nothing happens. It is using 30 watts, and I hear a little bit of humming. That will be the scope output. So let's see, what have I done? Oscillator off 10 times 10, 0, 0. Shouldn't that be about, I don't know, what am I doing wrong here? Because look at that. This is 100 hertz. This is a 10, and then this is the 0, so this is 100. But then why is this a times 10? I am a little bit confused. We got a little bit of dodgy connectors, but there's an output, but it's probably just me not understanding exactly what's reading here. I mean, times 10, we have 10 and a 0, so this is 100 times 10. That should be 1 kilohertz. And this is of course decimals. Okay, so that is 105 hertz. That is some weird stuff. So if I click this one, we got 1 kilohertz. Okay, whatever. That is some weird thing. Okay, so at least, so this is my output, and of course nothing happens at the moment because I'm only checking we got an output. So what I want to do is I want to take the output, put it into the input, and then attenuate the input here. Let's see. All that seems to be quite all right. Now it's using 100 watts. Did you see that? This is how this is why it is so insanely important to have an instrument like this set up and always look what you're doing. So it was using 40 watts and 100 watts, and then if I didn't turn off this fast, we would have seen a little kaboom and smoke and what not. Now I need to hunt down the problem. It is so easy to hunt down problems with a thermal camera. Here at the back we see two hefty capacitors, and they're not supposed to look like that. One is red and the other one is black. So here is your problem: a shorted capacitor or half shorted capacitor, and you really need a thermal camera. There's no need to look at schematics and no need to touch dangerous stuff. You can see it that easy. Haha. It cannot be me who is absolutely crazy. We have just seen thermal pictures, and it was the big one that was running warm, right? It was the left one, because when I unscrewed this one, it was still warm. I mean, it has to be that one. So what is going on here? Because the capacitor is not broken, and the 4 diodes here, it's actually 2 identical power supplies. I don't know if that is possible to see, but we got everything is completely symmetric, identical, and all that fancy smancy fine thing. And the 4 diodes, they are exactly the same, perfectly fine. Why is this capacitor running warm? That is a little bit of a mystery. There is a red wire that is the shield winding of the transformer. What if there is a fault inside the transformer, so the shield winding is connected to some AC volts? Then you have AC volts through that capacitor. But other than that, I cannot come up with any good explanation. Let's show the schematic of the power supply so you can see exactly what I'm talking about, the 2 identical systems. And that red wire is looking a little bit interesting. Also, let's look at the circuit board layout. Here is, I believe, yes, that is the red wire. It goes to that point, and then it goes to the center of the, yeah, see there's a track there. Look at that track, isn't that funny? Why is it doing that? And I mean, look at the other tracks in this layout. Some really, really funny layout is going on here. Yeah, but of course this unit is really, really old, and this is done on transparent film and tape. So I can't blame them for the funny layout style. Let's try and test this capacitor. So positive here is the red. It's connected. Oh yeah, let me show you this again. It's a 40 volt rated capacitor. So here is 40 volts for you. And those 2 are in series. I just set a current limit of 1 amp. And there you have it. A tiny little bit of millivolts of leakage. And that is all there is to it. That's weird, isn't it? And if we take this away, we should have voltage on this one, right? So here is a little solder wire. Ooh, I mean, and it welds to the wire. I mean, there's nothing wrong with this capacitor. It's full of all the goody currents. Cannot let this mystery go. So now I take this capacitor, but there's some wires and connected it to the circuit. And now I got a voltmeter here so I can see what is going on. So first let's look at the DC. And let's try and see, where are we in the world? 64 volts. So that explains the problem. This is way too much. It is only rated for 40 volts. How is that possible? Now I think I found the problem. All this cleaning and shaking and moving the unit around, the mains selector switch has been flipped down to 115. How is that possible? I gotta give this a drop of glue. What the heck? I've never seen anything like that before. How can they be like that? See? We turn it on now and I got 30 volts. And the whole unit is using 10 watts. What a terrible, terrible thing. This absolutely crazy. How is this possible? Okay. We got output. We got everything good. And nobody died. And okay. It's a little bit funny to see that we got 30 volts of DC. And we're trying to make a 15 volts supply. We got 0.1 in a ripple, and this is at 220. So if I take the volume down, so to speak, so this is the input voltage, and then here we go. Now it's out of regulation. So 148 volts input before we have a problem. So it's using 7 watts now. So there's plenty of margin. But since it's using so little, that's probably why they're using those tiny little heat sinks. All right, but problem is found. What a lucky me. Now I can continue playing with this unit. I'm still trying to figure out how this is working. I think it is not working. Because normally what you do with these distortion analyzer, there's a set level. Okay? So we take the generator output and you run it through your amplifier and into the input here of the analyzer. All right? So the idea is you calibrate the level of your stimulating signal, and I can do this by turning here on the oscillator level. There is of course some time constants. Once you figure out exactly how to do this, so if we just wait a little bit, it's going to calm down. So I believe now we have a correct set level. So now the idea is you go to distortion mode, and into distortion mode it activates all the filters. And I start with 100%, so it should of course read nothing, right? I think there's something to do with the notch frequency. So the idea is, of course this unit can test, and this is really the special thing with this unit. I believe that the generator also affects the distortion meter, so that means I can of course test distortion at many different frequencies. I didn't read all the details in the manual. If this is not true, then I need to modify the frequency here, and then that should have a big effect on the readout here. So let me try and see what happens if I change the frequency. Okay, the meter goes berserk. So that is not, half of those switches are also not working. Maybe I should take another generator and play with, because this is definitely just too unstable to poke with. Yeah, let me do that. This unit is not working with my external signal generators. And I think I know why. This thing delivers a massive output, and my generator just don't deliver that much. So, so when I put this its own signal into it, then there's a readout. So the thing is, this attenuator here is definitely completely broken, and there's something here that is not working. I should probably go and check out the fuse on the back. Maybe that is the problem, because it is just so much way out. This is milli microvolts. I mean, and this one sends out a massive output. So it gotta be something like simple as that, right? I think I found something. Let's try and look at the meter here. And then at the same time, let's turn this a little bit crazy. I'm sorry about this, but I want to show you. I think it was this one. Let me see if I can focus on that. So when I poke this a little bit, see? Ooh. So that means we got all those op amps, and they're more or less, not that one. Nope, not that one. No. Yeah, here's a little bit again. So those sockets, they are maybe not the best after all those many years. Oh, by the way, did I show you this so deeply? If we look at the date codes on the ICs, and 1976, I think this is more or less all of the ICs. They read 1976, and the manual is from 1979. So maybe I got a new manual or something like that. I also see a lot of corrosion. You can see here on the tracks, and that is of course due to bad and wrong storage. Let's try and look in here and see what's going on. That is some good news. Look at that. We got some fuses. Ha ha. And what do you know? I think the left one looks a little bit broken. Let's try and measure this. So here is my little tester. Ooh, that's bad. This one is working. Oops. This one is broken. Okay. That was the one that I would have guessed was broken. But alright. I will change this one. And then we will be back. So let's try one more little go. And we already got input here. Let's do the set level and try and poke. Oh, it seems real nice and fine. So I'll put it to set level like that. And then we'll flip to distortion. Damn. I was hoping it would go down. And then, okay, so at least now we have the input here. Okay, so how about the distortion? Is it something to do with the frequency? Now we don't have any indication here. So what happens if what is, oh, look at that. Here I got a little bit. What if I go completely crazy here? So that means it really tries to so it interlocks with this one. right? Or there's just a tracking error. But at least now, well, hey, let's try my other generator and see if there's any kind of luck. So let's go back to set level there. Let's do the set level with this one. All fine. Distortion. And I didn't change anything here. Now, look at that. This is my frequency. And now signal goes down. So how is this happening? I don't understand anything about what is going on here. So this is 100 hertz. Okay, let's go back. That's because level is... Why is level not responding? So if I give it 1 kilohertz, it is... I mean, there's something completely dead wrong with this instruments. I mean, how about in volt mode? Okay, so now it should tell me what is the level, okay? It should not be affected by this one so much. And now let's play with the frequency. Okay, so 500 hertz. What? Yeah, okay. The input circuit, everything here is just not working in any way. And I don't have any of those special op amps on stock, so I think I'm gonna put this back into the garage. Darn it. So I was able to figure it out. So I'm still in this 1 kilohertz mode, and let's go and set level. I'm now using an external generator as the input, and I'm looking at the distortion output to my scope. This is what you see here, right? So 1 kilohertz input, level is adjusted, yada yada yada. We go to distortion. So now you have the distortion readout, which is not working, and that is the output here. So now let's try and change the input frequency. Now I dial it up from 1 kilohertz to, see, this is 1.8, this is 2.1. Okay, let's try and say 2. If I fine tune this, I can prop 2.3, 2.678. See, level goes down, 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 down at 2.9, and then it goes up, back up again. So the tracking between the generator and the notch filter system is not working. Somebody's been poking around with the alignment between these two systems. All those switches, they are double, and they control both the generator and the notch filter system. And that is the only problem there is. Other than that, the unit seems to be working. Haha! How cool is that? And there's another easy way to prove that. That is simply just to hit set level again, and there you have it. So now I'm using the notch filters at 3 kilohertz instead of 1. All right, I got a few more things I really want to show you, and that will be those really sexy components. I think I earlier in the schematic talked about calling them relays or up to couplers or something like that. That will be normal relays, but those are actually analog up to couplers, isolated couplers. What they do is you got a little LED and an LDR, light dependent resistor, inside this little package, and we got 4 of them over here, and this is how they handle isolated feedback using those in some of the op amp and feedback systems. It's really, really cool. Let's try and look at the schematic. Here is schematic for the oscillator part. If we zoom in here on U1 and U2, that'll be the oscillator op amps with all the timing capacitors, and that's what happens when you push the different switches on the front panel. And the output from U2 goes down to another op amp called U3, and that one drives an LED. And this is a part of U7, as you see here, marked with a little red arrow. And this one optically controls the resistance in the other one, marked with the other red arrow. And that resistor now changes its value depending on the light intensity. And that is in the feedback loop of U1. So that's making the signal stronger or weaker, and this way controls the amplitude no matter what the frequency is. So it's measuring its output and feedback and controlling the gain. A very nice and clever way to handle the oscillator. The main board schematic consists of 2 pages because it's quite a complex unit. I don't really plan to go into super detail about all the different blocks. We already figured out we got a buffer amp and input stage and all that with the attenuator systems. And of course the function switch we have already played around with. The AC meter amplifier. It's a little bit weird if you look in the upper right corner and see this AC meter amplifier. It's what do you think about the 6 diodes in the feedback to that op amp? I mean, why do you need that many diodes? So I find that a little bit funny, by the way. And we got an overload detector, the filters, where you select the different filters, of course, when you change between 80 hertz or 400 hertz, and then you have the tuning indicator, and the tuning indicator is made by a phase-locked phase detector, where it detects the error signal, and then it amplifies this and control 2 LEDs. On the next page, we see the notch filter section, attenuator, distortion amplifier, some buffer, phase null control, and the amplitude null control. And we got a little bit of interesting things going on in this schematic. I think we should zoom in on the notch filter. And here we see some of those LDR resistors I have marked here with red. And that's of course to control how the notch filter works in the different frequency ranges and frequency sets and all that kind of stuff. So that could also be one of the reasons for this unit not to work or to be so much off frequency, because those LEDs, they just go dimmer and dimmer and need more current to get this resistor going on the right way. So there's probably a good idea to replace all those, but I don't think they're really easy to get. So that is more or less how the schematic works. So that was more or less all I wanted to show in this video. Thank you very much for watching, and I hope to see you soon again. Bye bye.